scanning tunneling microscope. This is example 9.2 in your textbook. Okay, and the basic idea here is you have a probe, a needle that moves through over a surface. Okay, so you have the gap between the tip of the needle and the surface. The atom and the surface would be serves as there's a potential barrier there for your electron to traverse. That barrier, it has to overcome. It has to undergo tunneling. Okay, so as you move this tip, basically what you can do is you can monitor the change in the current, and what's called the tunneling current, and that would allow you to map the surface. All right, so you can do this calculation, sample calculation given in that in your textbook. So you're given the value of K2. You can solve for the value of K2 from V0 minus E. Right? And you're asked how much does the current change as your needle moves from 0.5 nanometers away from the surface to 0.6 nanometers away from the surface. Now the current will just be directly proportional to the transmission probability. So if you want to take the ratio of the two currents, then you just take the ratio of the two transmission probability. So it's a kind of a plug and chug thing. So you just go back to the expression for T. All right? And on page 290 of your textbook, there's a self-test 9.5 question pertaining to proton transfer reactions. Again, the idea there is if you have reactions that involve proton transfer, okay, they would be faster if you have protons rather than deuterons. What's a deuteron? A proton is H+, right? What's a deuteron? It's also H+, except that in your nucleus you have a proton and a neutron. Okay, so this is the hydrogen 2 isotope. Okay. Why would a proton transfer reaction be faster than a deuteron transfer reaction? A deuterium atom is heavier than a hydrogen, a protium. Okay, so a deuteron would be heavier than a proton, so it's less likely. It has less tendency to tunnel, less capability to tunnel.